some important properties of Christoffel symbols of first and second kind. Okay, so first property is partial differentiation of metric tensor is equal to this thing, means these are sum of Christoffel symbols of first kind. So proof is very easy. So proof of first. Okay, so right hand side equal to ijk plus jki, because we have already explained the definition of Christoffel symbols of first kind. Okay, so this equal to 1 by 2 del g ij upon del xk plus del g ik upon del xj minus jk upon del xi. Okay, plus now again using the definition of this thing, so 1 by 2 del g jk upon del xi plus ji del g ji upon del xk minus ki del g ki upon del xj. Okay, now by using the property of metric tensor Gij is symmetric tensor. Okay, so this is minus gki and here ik. So since gik is equal to gki, so this is minus and this is plus. And similarly ik upon jk upon I and here jk upon I. So this and this. So 1 by 2 ij upon xk and 1 by 2 del g ij upon xk. So this is del g ij upon del xk. Okay, and hence proved. Now what is the second property? So this is second property. So now I am going to prove second property. So second. Okay, so second property means partial differentiation of metric tensor in upper, means contravariant. In the ijk here covariant. Now we shall prove for contravariant. Okay, so we have gij ik is equal to Kronecker delta I contract kj. So how we shall prove? So by using the known property, means I already obtained the result del gij upon del xk. Okay, so we shall use this result. So firstly we have gij gik is equal to Kronecker delta kij. Now differentiating partially with respect to xl, differentiating partially with respect to xl. Okay, so there in left hand side these are two function, means product of two function. Okay, so del xl gij and second as it is plus first function as it is del xl gik. Okay, in right hand side, since definition of Kronecker delta is either 1 or 0, in both the cases 1 and 0 are constant, so partial differentiation of right hand side is 0. Okay, now we need to calculate this value. Okay, so gij and del xl gik is equal to minus sign del xl gij into gik. Since this is known value by the first condition, so first we put the value of del gij upon del xl and then we solve. Okay, so now putting the value of del Gij upon del XL. So we get Gij del XL Gik equal to, so this is minus Gik. The value of this thing equal to IJL plus JLI. Okay, so now this equal to, now multiplying by Gik IJL minus Gik JLI. Okay, now we need to calculate this thing, means partial differentiation of Gik upper. So here we need 1. Okay, so now multiplying by Gjm. So since we need to 1, so we want to calculate this thing. So Gij, how Gij is 1? So our thinking is that, means first we go to about chronicle delta. Okay, so by multiplying Gjm, so if we multiplying by Gjm upper, so Jj contract, so chronicle delta Mi. Okay, so by multiplying by Gjm Gij del XL Gik equal to minus Gjm Gik IJL. Okay, and minus Gik Gjm and JLI. Okay, so here J and J contract, so he chronicle delta Mi in left hand side, and del XL Gik equal to, and here by definition of Christoffel symbols of second kind, I contract, so minus Gjm Christoffel symbol KJL, and similarly here J and J contract, so Gik Christoffel symbol JJ contract to MIL. Okay, so now if m is equal to 1, then this is equal to 1, otherwise 0. So here put I is equal to m. So del XL Gmk equal to minus Gjm KJL minus Gik Christoffel symbol MIL. Okay, so this is very easy to see MKL. So here MKL JJ contract, MKL II contract. So this is the proof. Okay, now we shall prove the last result, means Iij gamma Iij is equal to del J log root G, means proof of third result this. Okay, so proof is very easy. So we have in any metric ds square is equal to Gij dxi dxj. Okay, so here Gij is called metric tensor. So we have Gij in matrix form. Okay, Gij in matrix form. So Gij equal to G11, G12, G13, G1n, G21, G22, G2n, and Gn1, Gn2 in Gn. Okay. So the determinant of this matrix is mod of Gij is nothing but we denote G is equal to G11, G12, G1n. Okay, G21, G22, G2n, Gn1, Gn2, Gn. So this is the determinant. Okay, now differentiating with respect to xj. Okay, now differentiating with respect to xj partially, so we get differentiating with respect to x, because I have taken here I and j, so other index xk. Okay, so differentiating partially with respect to xk, so we get del g upon del ax k equal to, so you know the differentiation of determinant. So first of all we differentiate first row and then second row and then third row. Okay, so first row is this thing, so by del g11 upon del ax k, del g12 upon del ax k, del g1n upon del ax k, and other rows are as it is 2 1, 2 2, 2n. Okay, and last is n1, n2, gn. Okay, plus now we differentiate in second row. Second row means G21, G22 and J. So all the rows are constant, only we differentiate in second row. So G11, G12, G1n. Now del G21 upon del ax k, del G22 upon del ax k, del G n1 2n upon del ax k, and remaining rows are as it is gn1, gn2, gn, this plus dot dot. In the last we differentiate last row, so g11, g12, g1n, g21, g22, g2n. Now last, so in last del g n1 upon del ax k, del g n2 upon del ax k, del g n upon del ax k. Okay, so this is the, so this equal to, so first we solve first term and then second term and then last term. So you see first term, so we calculate determinant. So how we calculate determinant? So this is equal to del, first we take del g11 upon del ax k. Okay, and then cofactor of all the things means cofactor of del g11 upon del ax k. Okay, so this equal to del g11 upon del ax k, and then cofactor of del g11 upon del ax k plus del g12 upon del ax k and cofactor of del g12 upon del ax k plus up to so on, and similarly del g1n upon del ax k cofactor of del g1n upon del ax k. So for the first determinant and similarly second determinant and similarly last, so there are number of terms are n by n, means n square terms. Okay, So here we see that cofactor of del G11 upon del xk is nothing but cofactor of G11. Okay, because here if we calculate cofactor of del G11 upon del xk, so we put only we take these things, means this row and this column. Okay, we drop this row and this column, and so similarly cofactor of G11 the same thing. Okay, so plus now del G21 upon del xk into cofactor of del G21 upon del xk, and similarly in the last del G n upon del xk into cofactor of del G n upon del xk. Okay, so now since we have cofactor of del G11 upon del xk and cofactor of G11 is same. Okay, so del G11 upon del xk into cofactor of G11. Okay, plus in the same thing we put in place of cofactor of del G12 upon del xk is G12. Okay, del G12 upon del xk into cofactor of G12 plus up to show on del G1n upon del xk into cofactor of G1n plus up to del Gn upon del xk into cofactor of Gn. Okay, since cofactor of del G11 upon del xk is equal to cofactor of G11. Okay, etc. means for all the things. So now this equal to, this can be written as del Gij upon del xk into cofactor of Gij, cofactor of Gij, because there are n cross n term, so by Einstein summation convention this can be written as this thing. Okay, also we have Gij is equal to cofactor of Gij in G upon determinant of G, means simple G. Okay, so now this can be written as del G11 upon del xk cofactor of Gij. So cofactor of Gij in G is equal to G into Gij. Okay, so del Gij upon del xk equal to, so in this place G into Gij, so G into Gij. Okay, so now in left hand side here del G upon del xk is equal to G into Gij del Gij upon del xk. Okay, now dividing by G on both sides, so we get 1 upon G del G upon del xk is equal to Gij into del Gij upon del xk. Also we have the value of this thing, since del Gij upon del xk by the property of Christoffel symbols of first kind, this is equal to I jk plus j k I. Okay, so now putting this value, so this equal to 1 upon g del g upon del x k is equal to g I j I j k plus j k I. Okay, now gij in both the terms, so gij I j k plus gij j k I. Okay, now again applying the definition of Christoffel symbols of second kind, so this is I contract, so this is j k plus j contract I k. Okay, now since this is dummy index, so dummy index can be changed any other index. So if we put in the place of j is I, so this is I k plus I k, means this is equal to 2 gamma I k, means 1 upon g del g upon del x k is equal to 2 times gamma I k, and 1 upon g del g upon del x k is nothing but, this is nothing but, since differentiation of del by del x k log g is equal to 1 upon g del g upon del x k. Okay, so this is equal to del upon del x k log g. So by dividing by 1 by 2, this is equal to 2, so I k. Okay, so again by property of log, n log m is equal to log m to the power n, so gamma I k is equal to del y by del x k log root g. Okay, this is log root g, this is nothing but log root g, because n log m is equal to log m to the power n, so this is del upon del x k log g to the power half. Okay, so this is equal to del upon del x k log g. Okay, so and hence proved. So if g is negative, so here we take minus g. Okay, and hence proved.